lines within each proton NMR signal. So remember, for the first approximation, you're just counting the unique sets. For your second approximation, you have to look at the number of neighbors to see how the signal splits, and that's called multiplicity. So we'll look at the reason why that is, and why the lines in doublet, triplet, quartet all have different intensities. So we'll spend the first about 15-20 minutes doing that, and then the remainder of the lecture looking at another putting it all together problem where we have mass spec, IR, NMR, where we're going to figure out the instructions. Any questions before we get started? Other than why does the projector not work? So here were the two structures that we were talking about, this ester and this ketone. And we know now, looking at proton NMR, we can pull some things out of what's important. So here's the ester. So overall, we can see there's, a signal here at 4.18. Signal here at 2.94, so those are two signals. The number below, that's the ratio or integration. And so we have those two CH2 groups. And then based on the chemical shift, we can make some assignments. So we'll say the blue triplet belongs to that CH2 group. And then the green one here belongs to that one based on the substitutions that they've done to push the chemical shift away from zero. And so since each of those is a unique set, you look to the neighbor. They each have the two neighbors, so 2 plus 1, that's your triplet. And within the triplet, we sort of draw a line. We can say that, 1, 2, 3 lines for the triplet. We can say that the center line is twice the intensity. So that's in a 1 to 2 to 1 ratio of the height. And so that's what we'll talk about today, is why does it have that intensity of the lines? And the same analysis for our ketone. We can say that the CH3 group here is going to be the singlet because there's no neighboring hydrogens. So in green, the quartet, because it's showing 4 lines, that means the neighbor has to have 3 hydrogens, so that's going to be the CH2 group there. And then finally, the methyl group, that has 2 neighbors, so that's going to be a triplet. And again, the numbers under there, that's 2 hydrogens, 3 hydrogens, 3 hydrogens. The chemical shift is important. It tells you the environment in which it's in. So we're going to talk more about the nature of these multiplets. You'll look at some pretty pristine examples of them and why the lines have the intensities they do. So again, your first approximation is determining the unique sets of H. And so if you say there should be 3 signals, then you're going to look for those signals, and then your next approximation, you have to do the n plus 1 of the neighbors. So in our list here, if there's no neighboring hydrogens, 0 plus 1 is 1, so you get a singlet, and we say the intensity is just 1. Keep in mind, from one of the quiz questions, the the shape of this signal is not telling you how many protons belongs to that signal. That information is telling you about the neighbor. So you can have a singlet that's, 1 hydrogen, 2 hydrogen, or 3 hydrogen for the ratio. So you have a one neighbor, 1 plus 1 is 2, that's a doublet, and the intensity is 1 to 1. And then the pattern here in this last column, that was Pascal's triangle. Where basically the edges are always 1. And then, for example, when you get into 2 neighbors, now you have 3 lines, so you have a triplet. The 2 comes from 1 plus 1 gets you 2. And so as you go down in these rows, you go back to the prior row and add the digits moving across the line. So we can see 3 neighbors, 3 plus 1 is 4, that's called a quartet. So again, the 1s are on the outside. The 3 here comes from 1 plus 2 gives you 3, 2 plus 1 gives you 3, and then you end with 1. And that is telling you the intensity of the lines in the quartet. So again, that's really so far sort of empirical. You can relate the intensity of those lines back to this mathematical function, I guess, but what's the reason why it's like that? So when I'm talking about intensity for this singlet, if I'm just looking at the height there, we can just say that's 1. So for a doublet, if we draw a line across, when we say that's 1 to 1, that's the intensity of those lines to one another. Then the triplet, if we start with the lowest, we say it's 1 to 2 to 1. So that's what that means. Quartet, 1 to 3 to 3 to 1. And then the higher order ones, you can see as you add more lines, the sort of like little peaks at the end become smaller, and they're almost buried in the baseline. So for example, these little blips here, they don't really rise too much above the baseline. So what is the reason for this? And again, this is a very simple explanation of why this happens. To be NMR active, the nuclei must have an odd sum of protons and neutrons to give rise to the nuclear spin. And again, that's what's detected. So it's 1H, the 1 is odd, or it's 13C, the 13's odd. The way the instrument is set up is there's a magnetic field, and from physics they use this B0 as the vector for the external magnetic field. And when you put your sample in there, the nuclei, as shown by this blue vector here, will either align with that field or they'll be spin opposed. And so the difference between those two is the energy state. And we talked about the operating frequency of the instrument. That basically relates to this value here. So you have these spin states for specifically proton. So it can be one of two spin states, with or against. And so why does the splitting actually happen after you sort of determine your unique number of sets? So empirically, we saw that we use the n+1 rule. But again, why is that? It's due to these spin states. So again, if this is your signal of interest here, that is impacted by the number of neighbors. So if there's one neighbor, you get 1 + 1 is 2, because the spin states of those neighbors impact that first approximation signal. Does that make sense? I'm getting some very scary looks from the audience here. So again, let me draw, here's your, say that red arrow is your external magnetic field. If you have one neighbor, the spin state can be aligned with it or opposed to it. And what that is doing is taking that single peak and it splits it into two, because each of these are considered like a little magnetic field that's either going to add or subtract to the signal you're seeing. So one of the spin states sort of pulls it this way, the other pulls it that way, and that's why it looks like a doublet instead of a singlet. And so this happens, as you increase the number of neighbors, now the combinations of spin states can increase. So we said that for two neighbors, you get a triplet. This is a 1 to 2 to 1 ratio of line intensities. And so if you have two hydrogen neighbors, then you look at what their spin states can be. So they can both be up, or they can both be down, or you can have a combination of those. So one up, one down, and then one down and one up. And so this 1 to 2 to 1, that's what that's referring back to, is these combinations of spin states. So here's 1, here's 2, here's 1. So all of these nuclei, when they spin, they act like little magnets that affect the signal of interest. And so what they're doing is your first approximation, they're pulling it sort of downfield and upfield, and then based on the number of combinations, you get a doublet, triplet, quartet. So there it is with the little vectors drawn in to show you that. So again, if you pay attention to sort of this center line here, those spin states are either shielding or de-shielding your original signal. So that's why you get this separation. So let me draw this in real quick as best I can. See this distance here, and then this distance here. Those are going to be equal distances. And that's called J, which is the coupling constant. And that's reported in hertz. It's constant because no matter what instrument you measure it on, that value will always be the same. So a quartet, you have three neighbors. You have this 1 to 3 to 3 to 1 ratio. So that the outsides are kind of easy. So if we draw them all spin spin up or aligned, spin down or against. So there's your 1 and your 1, and then in the middle you have the 3 and 3, and that's the possible spin state combinations. So say 2 up, 1 down. So this one we need down, down, up. And that's just a little arrow representation of what's happening. And there's your ratios. So as we look at more of these spectra and do problem solving, you'll find that like fragments that are sort of blocked will always have like a unique signature to them. So there's the slide with them drawn in. Like this line right here.
Yeah, like why would it not have all 6 of like three?
I guess the way that I think about it is when you're downfield, all 3 are aligned. When you're upfield, they're opposed. And so to get from there to there, you're sort of switching one at a time. So notice how you have 3 up, then you have 2 up and 1 down. And then the 3 comes from, you're just moving the down arrow from each hydrogen.
So it doesn't have like you get
No, I don't think you can overlap them in the way you're saying. Let me sort of explain what I mean by that. So I think we saw this on a quiz, ethyl acetate. So when you look at it, there's 1, 2, 3 unique H sets. And so of that, I'm going to say there's 2 spin systems. And the way that I can say that is if you look at this methyl group, you see it has no neighbors, so it's blocked. And so that's its own little thing. So that has to be a singlet. sp2, then oxygen. Then you have this CH2, CH3. So that spin system, it's blocked by this oxygen, right? Because there's no neighbors there. The sets in that fragment do not communicate over to that fragment. So that's why we can say they're different spin systems. So if we examine this OCH2CH3 as its own system, that's an ethyl group. And so what signatures, what multiplicity should this CH2 have? So that's a quartet, and then the CH3 is going to be a triplet. So that's what I mean is like these fragments, if you see a quartet in a triplet, you can say, okay, those 2 things are coupled to one another. And really, what does that mean? I'll draw it a couple different ways here. So again, that signal appears as a quartet because of these three hydrogens, their spin information transferring back to this signal. And the way that I think about this is sort of, they're just talking sigma bond, sigma bond, sigma bond. They're talking through that sigma bond system. And so I'll crudely, crappily draw a quartet here. So quartet, triplet, that spin system is coupled. The CH2 talks to the CH3, the CH3 talks to the CH2. We understand now the reasons why the lines have the intensities, and then the distance between these lines. So what I marked in blue, that has to be the same distance within that signature. And it also has to be the same distance here for the other one. So that's why it's called a coupling constant, because those two signals communicate to each other. So blue line, all you're doing really is taking the parts per million here, the parts per million there, and you subtract those numbers. Then multiply it by the operating frequency and you get hertz. So it's Friday, I don't want to fry your brain too much. But the value of that can be between 1 and 15, the coupling constant. And so now there's something on Monday that we'll go into even further is the angular relationship between these hydrogens. So sigma bonds can rotate. So these things are rotating. They come out to an average angle. And the value for those in terms of the coupling constant is about 7 hertz. So that value of coupling will change depending on the angle of the hydrogens that are talking to one another. Yep.
On the last slide with the states, like the orientation.
So the point of this is when you look at the signal, what again it's telling you is the number of neighbors that are influencing that peak, and then what we'll learn on Monday and Wednesday as well is the distance between the lines in the signal tells you about the angle between the protons that are talking to one another. So you might think, well, how is this relevant to the functional groups I know? If you consider propene, you might first say, well, this carbon has 2 hydrogens, so that's one set. This has its own, that has its own, so there's 3 sets, but actually that's incorrect. The total number of sets here would be 4. If we look at HC, its angular dependence to HA is different from the angular dependence to HB. So HC couples to HA versus HB differently, which makes A and B not the same. And so that's what I mean by how the angle influences the magnitude of the coupling constant. So what we'll finish off today with is looking at this data set and then trying to predict a structure. So this time we'll actually go through all these questions one by one, so you can see the logic evolve through it. But again, at this point, you should be familiar with, identifying that's an IR spectrum. This is mass spec, carbon, proton, and what are the key signatures we want to pull away from. So I won't write too much on this. We'll just walk through the slides to show you the sort of bigger pieces of information we want to pull out first that can help us start to put together a molecular formula again. That's under that black mark. That's the molecular formula. That's the first thing to determine. So looking at the IR, the mass spec, and the proton NMR, what combination of heteroatoms is present? C. So bromine and oxygen. So if we look at the parent ion in the mass spec there, we see that there's M is 172, and then M plus 2 is 174. They're in a 1-to-1 ratio, so that's indicative of bromine. The mass is not odd, so we can eliminate nitrogen. And then the IR here, that's really looking like an OH of some sort. So we can say bromine and oxygen. And so thus far, the way that I like to do this is just write sort of little fragments. So there's bromine. We can say O like this. We know there's an oxygen. The other thing in the proton NMR, it says exchanges with D2O. And as I mentioned last time, those are typically hydrogens bonded to a heteroatom. So if we know that there's oxygen, we know that that's telling us that there's a hydrogen associated, so it's an OH. So we can revise that to say, okay, there's an OH. And so, we're sort of piecing the molecular formula together here. So we could write something like that at this point. We know there's bromine and oxygen, and carbon and hydrogen are given. And so you can look at the number of signals in the carbon and count how many carbons there are, but I'm just showing you another way to do this. It's basically saying if the parent has a mass of 172 and we figured out that there's bromine, oxygen, so we'll subtract those out and then we'll get some value, divide that by 12, and that's going to give us an estimate of the number of carbons. So I definitely can't do that in my head. So that's 77. Huh?
We use 78 for the bromine because we're only accurate. Oh, that's fine.
This yes is BPR.
Yeah.
So if we take 77 And so divide that by 12. It's going to get us 6 carbons. And so to figure out for this question, 12 times 6, that gets us 72. So that's the carbon contribution. Did I do something wrong?
But it also indicates that there's a nitrogen is odd, or
No, because it's the parent is 172, because we already subtracted some stuff out. So this is the other way you could do that, is you just count the unique number of carbons. So here's the carbon NMR. We ignore the solvent. We can count 1, 2, 3, 4, 5, 6. There's 6 unique carbons. And then I showed you last time this other thing called the depth, where it's stacked above the carbon NMR. And the phasing is odd. So CH3, CH are phased up, CH2 is down. So when you look at that, you can say there's no CH2s in this molecule. What else can you say? How do you interpret? See how there's 6 and then there's only 4 here? So what are those two? Just C. They have no hydrogens attached to them. So 6 hydrogen or 6 carbons, 2 with no H's. And so evaluating the location of the chemical shifts of these signals, how many of each type of hybridization are there? So the line that you're looking for is about 100. And the SPs fall sort of in between there, 80 to 100. But if you look at that, you're well above 100. So these are all sp2 hybridized carbons. And if they're sp2 hybridized carbons, so we're going to get A is the answer. What does that tell you about the 4 signals you see in the depth? So if we said CH3 and CH are phased up, what do those have to be if the carbons are sp2? They have to be CH. You can't have an sp2 hybridized carbon with 3 hydrogens. So these are all sp2H. And so now you have a little bit more fragments that you can start putting stuff together with. So we answered this one. It was 4. Again, these ones at the end with the X's on them have no attached hydrogens. Those are 4 CH groups where that carbon is sp2 hybridized. So excluding the signal that exchanged with D2O, which we're going to attribute that to OH, how many unique signals do you observe in the proton NMR? It's going to be 4. So this right here to the right, that is just a blow up of that region. So you have 1, 2, 3, 4. You can kind of see what their structure is, right? So this first one, this is a doublet, this is a triplet, this is a doublet, that's a triplet. You got a little like sort of Mordor horns on them. I call these Mordorplets. That's just finer splitting. So the coupling is sort of, there's more of it. But you can tell by, okay, that first thing is a doublet. So therefore it has how many neighbors? 1. And so that's, you're sort of reversing back and piecing this together. So you have 4 signals where the H is bonded to carbon, then you have 1 where it's bonded to oxygen. So yeah, if you look at it, doublet, triplet, there's no singlet, so it's telling us it's the 1-2 substitute. And so I'm gonna just tell you the C6 belongs to a benzene ring. So that's benzene. There was an alcohol, we figured that out from the IR. And there was a bromine, we figured that out from the mass spec. There were 6 carbons, and then we figured out from the proton there were 4 signals. The ratios were all 1-to-1 to 1-to-1. And now the issue here is on that benzene ring, we need to stick the OH and the Br. And there's 3 ways we can do it. So that's called the 1-2. This is the 1-3. And that's the 1-4. So we're trying to figure out which of those isomers that data belongs to. So it says, how many unique type of hydrogen sets does each constitutional isomer have, excluding the OH signal? If we, huh? Well, we need to figure it out for all of them. If you look at the 1 and 4, this basically has an element of symmetry where these hydrogens are the same and then these hydrogens are the same. So we're going to ignore that H one for now. So the 1-4 has 2 unique sets. So we can eliminate A and C. Now let's just go back to the 1-2. We're not counting that H. We go on to the ring. There's 1, 2, 3, 4. These carbons at 1 and 2 were the ones that did not have hydrogens attached to them. So that has 4. So it looks like we can eliminate D. So our answer is going to be B, but let's verify that the 1-3 also has 4 unique signals. 1, 2, 3, 4. So the issue now is you see how the 1, 2, and the 1-3, they both have 4 unique sets. What else can we use to differentiate them? And that's going to be the multiplicity of those sets. That's how they'll differ. Pattern. So let's draw them out and do the neighbor group analysis. So we'll just write a little letter next to each H. So this hydrogen, it's a unique set. We consider the neighbors. What should it end up being? It has 1 neighbor, so it's going to be a doublet. So the next one has 1, 2 neighbors, so that's going to be a triplet. The next one there has 1, 2 neighbors, so that's also a triplet. And then finally, the last one just has the 1 neighbor, so that's a doublet. So we have DDTT, so that eliminates A and B for that one. So let's look at the 1-3. We'll do the same analysis. If we start there, that hydrogen has no neighbors. That's a singlet. So right there, that is the difference between the two, because the other one does not have a singlet. This H is a doublet. That H is a triplet. That H is a doublet. So because that needs a singlet, we can eliminate D, and C will be the correct answer. So really between the 1-2 and the 1-3 substituted, the special thing to look for is that singlet, is how you differentiate them. So even though I don't have the data up there, you know, the answer I believe is A. Let me scooch back. So we eliminated C because there was more than 2 unique sets in the proton. We eliminated D because there was no carbonyl in the IR. B was eliminated because there was no singlet to it. So this slide just summarizes everything that we walked through with that. I know it's a bit much, but you know that's basically how it's done. And again, the importance of this is when you're learning reactions that can produce more than one product, you have to figure out what is the major product. And so, as we saw with this, it really came down to the multiplicities of the signals. So I think the rest of these slides are just walking through that. Forward. Logic. I know it's a bit early. I definitely want to give you your money's worth. Are there questions? No questions? Chick-fil-A is calling. The daily pilgrimage. All right, don't forget your quiz is open. The Friday quizzes have a lot lower participation, so please don't forget about it. Make sure you do that. And I believe your exam for the NMR is next Wednesday. So we'll see you next week.